Good afternoon, everyone. First of all, I'd like to thank Ashraf for the kind invitation and also for your time and interest for the seminar. Today I'm going to talk about the topic on organic solar cells. I think this probably is one of the best research center in the world in organic in photovoltaic in a way, and we're working on the organic solar cells. I know there's also a large group of people working on organic solar cells. So there's some interesting progress going on in this field. And today we'll be discussing about some of the research work we did on the semi-transparent organic solar cells. So this is the outline of my talk. I will give a very brief overview of organic photovoltaic technologies, and then I'll be discussing about the transparent electrode. In the field of organic solar cells, transparent electrode is one of the key components that determines the device performances, and I'll discuss about the what is the optical way of how to enhance the light absorbance in the very thin organic stack used in solar cells. And I'll be also discussing about the concept on semi-transparent solar cells, and give a summary on what the performance of the solar cells and applications that can be used. So solar cells essentially is a device that converts the light into electricity, and there are many different ways to clarify types of solar cells. And so here, if I briefly mention that maybe solar cells we can be classified as a bulk type, thin film type, and the ones in the yellow boxes essentially represents the inorganic high efficiency solar cells. Those solar cell technology essentially already penetrate into the field. We already see many of the silicon-based solar cells being in the field, and more recently they've been used for grid connections to generate powers, because we know that solar energy is the renewable and more sustainable energy sources. But in terms of the wide area, the applications, in terms of efficiencies, silicon-based solar cells, silicon still dominated in terms of efficiencies as well as the lifetimes. But more recently, research into thin film-based solar cells really attract a lot of interest. Primary reason is that bulk-based crystalline silicon solar cells still relatively expensive compared to the gas-generated energy, electricity, for example. So really looking to use less materials and maintaining good cell performances, for example, using thin film silicon-based solar cells and 2,326 compound semiconductor thin film solar cells, and etc. So essentially, in terms of technology-wise, thin film solar cells and bulk silicon-based solar cells, essentially they're the same, using PN junction or PIN junction amorphous silicon solar cells. And it's really looking to a new area, because we are not only satisfied with the current technology, so we're looking to the new way of generating electricity from sunlight, whether we can generate light in a more cost-effective way, or whether the solar cells can be prepared into a more simple techniques. And really the organic, if I would group them in another boxes. So compared to silicon-based or thin film silicon-based inorganic, traditional inorganic solar cells, this is relatively young. Organic solar cells can be including the dye-sensitized solar cells, or polymer organic hybrid solar cells, and using solution prepared polymer materials, or sublimation of small molecule solar cells. And more recently, the nanoparticles, nanowires, quantum dots concepts are incorporated into the solar cells, with the whole aim or ideas, hope that we can make use of the solar cells in a more efficient way and at a low cost. So really, organic solar cells is relatively young and new, and compared to the traditional solar cells technologies. So this is something that we're quite familiar. We see a lot of standalone systems and solar farm. Some of them are all grid connected and have been widely used and generate electricity, clean energies to improve our life quality. This is the dominant technologies, and probably we can also explore and look into other forms of photovoltaic technologies. And so in addition to silicon-based solar cells technologies, there are other types of thin film based typically. For example, our copper indium gallium diselenide, CIGS, this has been proven not only in the lab and also in the production, that showing power conversion efficiency in the range of 10 to 15%. But really, if you look in the large area, solar farm type, this technology still faces a challenge because the resource of indium is not abundant on Earth. So that really is threatened for the future of CIGS, although the efficiency-wise this is very attractive. Cadmium telluride is another form of thin film solar cells with a proven power conversion efficiency of 10 to 15%, even in the large scale. And but we know that in terms of other materials, cadmium seems not so friendly in environment protection. So we need to handle this material very carefully. And also, if you look at the large area, tellurium is also could be potential supply issues, and because we don't have many of those materials. And look at the other technique called dye-sensitized solar cells. This is typically using a solution-based, essentially using titanium dioxide materials and using dyes, and it works in different illumination conditions. Particularly, it has less sensitive to the angular dependence of the incident light. But in the lab, the efficiency of a dye-sensitized solar cells has really reached to the 10 to 15%. But the high efficiency DSSC or dye-sensitized solar cells essentially works with liquid electrolyte, ruthenium. This is essentially a very expensive material. So if for a large area based panel or solar farm, if you have a liquid incorporated in the solar cells, it may have a potential challenges in lifetime issues. So for some applications, this is very useful because low cost, extremely low cost, and you can change various colors, depends on the dyes that you use. And people have tried even using fruit juices to produce very nice DSSCs. So the next device technology is called organic solar cells. This in general includes polymer-based and small molecule-based semiconducting materials, because these materials are essentially man-made, human-made, and synthesized. So in terms of selectivity of the materials compared to the conventional and inorganic semiconducting materials, you have a large varieties of material you can choose around. You can synthesize various materials with tunable electrical or optical properties. And in the lab, it has already demonstrated for single junction organic solar cells, the efficiency is already reached to close to 10%. This is very attractive. The one thing is that the entire thing is a low processing temperature and solution based, because DSSC, although it is a solution processed, but the synthesis of dyes titanium oxide requires very high temperature. So, but in this case, is that you could probably do it at a room temperature. So potentially it's very attractive. Potentially it could be a low cost, very efficient, And stability-wise, currently is a challenge because we are still working on it. And one of the challenges this class of materials faces is that organic solar cells, we know, has organic semiconducting materials in general has a relatively narrow responsivity compared to the conventional inorganic solar cells or materials, semiconducting material. So this could be a little challenge. But in general, if you are using several different types of organic material, semiconducting material, blend them together, or you do in a stacked form, so you can use several organic semiconductor with narrow spectrum, so long as they don't overlap each other, you can still combine them and make possible for high efficiency. So that's why this is really an attracting topic to explore working. This is how. So here I'm share with you some of the main difficulties or limitations organic solar cells face at the moment. Mainly, as I mentioned, P3H PCBM. This is the main the system that people have been widely reported. So and in the beginning of the work, we choose this system because we have there are a large amount of data available for comparison studies, and you will see that it has a relatively short or narrow absorption spectrum, and although the material itself has relatively high the absorption coefficients, we know that the maximum output the photocurrent density is proportional, depends on the absorbance. So you can imagine that if the material only absorbs a small part of the light, there's a limitation in photocurrent generation. So the other part of the organic semiconductor is that the carrier mobility is very low, a few orders of magnitude lower than that in the semiconducting material. So this is another limiting factor, I know, for relatively poor performance. So in this field, synthesize new materials is one of the challenges, and also because of this limitation, even though a material can absorb a lot of light, in the reality, the thicknesses of the active layer used in organic solar cells is typically less than 200 to 300 nanometers. Okay. So there are other issues. So I'll give you an example showing what is the problems organic solar cells face. So this is the typical absorbance of P3H to PCBM blend. Theoretically, it absorbs almost 14% of the light, incoming light. But when you turn it into the devices, in terms of power conversion efficiency, probably the representative and most respectable power conversion efficiency for that system is close to 5%. So where does the light loss to? And essentially there are a lot of issues in organic solar cells where many people around the world and explore to look into the ways to improve the power conversion efficiencies. So for organic solar cells, from materials and device point of view, probably these are the hot topics, the key areas where we are looking into. First is synthesis or explore, looking into low band gap photoactive materials that it can hopefully the absorption will expand to the near infrared range, therefore transfer to high photocurrent densities. The second way is that because the nature of the material has a very narrow absorption spectrum bands, so therefore probably tandem solar cells is approach. For organic solar cells, tandem devices is relatively easier because you're essentially spin coating and coat more layers with different absorption, and then there can overlap and response to solar in the solar spectrum in the broad range. So therefore, to improve the efficiency. And the third approach probably looking to different ways to improve the light harvesting, or we call it in-coupling features. There are many different techniques. So these are essentially technically wise, the technical challenges organic solar cells are facing. But in addition to this, we still see a lot of potential advantages that organic solar cells has. Now, first one is obvious that essentially you don't need to have a very expensive system or vacuum environment to fabricate these cells. They can be solution prepared and very lightweight, because essentially the whole layer is within the range of 200 nanometer to 300 nanometers, and it can be made into semi-transparent, and can be also fabricated on flexible substrate. So potentially really offers additional options for low-cost photovoltaic devices. And if it's a solution processed and also can be fabricated on flexible substrate, so essentially this row-to-low fabrication concept can be incorporated and essentially can reduce the production costs quite significantly. And the other things that people talk about is a payback time, because the energy, amounts of energy that you invested to produce solar cells, essentially you need to pay for whatever the energy that you generate by the panels. So this is relatively low energies involved in produce energy. So here showing the potential applications if the things can be, organic solar cells can be fabricated into semi-transparent or transparent, and then it can be used as a curtain, for example. Maybe in future, the tinted glass can be a layer of semi-transparent solar cells, so it allows the visible light to pass through, and also capture the near-infrared light, or the light that we don't want, to recycle them for power generation. So this is the typical devices that we made. It's semi-transparent. You see that you can see through. This is one of the very early devices we made. This was made in sublimation technique. So later we move on to fabricate the devices into using solution technique. So we see that the advantages and of these technologies, and also we see a lot of the challenges or limitations that I mentioned a few slides ago, because the advantages and challenges always come together. So really, and while we appreciate the advantages, and probably we also are facing some of the technical difficulties. So for organic solar cells, perhaps we first thing is looking into conducting materials, which responds to the longer wavelengths of the light in the solar spectrum, therefore to harvest more light, and looking into the materials with tunable electro and optical properties. And second one is understand and how does this charge being collected, because essentially in the end we still need to deposit the electrode. So organic semiconductor and electrode interface that really is not fully understood at the moment compared to conventional inorganic based solar cells. So from device point of view, light harvesting and solution processability, how do we do, what kind of the solutions, solution additives so will be used, and the last is more important for organic solar cells, which is encapsulation. How do you seal them appropriately so that they can work because most of the organic semiconductor, they're not typically happy to be operated with the presence of oxygen, for example, or moisture. So you need to keep those things away while using them for various applications. Okay. So in general, from technical point of view, we see that assume that this orange color box is an organic solar cells, and then we have light comes in, or the photon receives the photon, and then in the end, on the other side, you just collect and count how many charges are being collected, and then you divide the ratio between the two, essentially determines the external quantum efficiency of an organic solar cells. So you know that from photon, you convert photon to charges. There are many different steps, so converging steps. For organic solar cells, the light is absorbed, and because organic materials has a very large dielectric constants, not like inorganic semiconducting materials, silicon, for example. So upon the illuminations, you won't get free charges, power generated. In organic semiconductors, the excited states, excited holes and electrons always appear in pairs. They're called excitons. So these excitons need to diffuse and find a way to decompose, and usually they decompose at donor-acceptor interfaces, for example. But during the processes, diffusion found a way to decompose effectively, become independent holes and electrons. They very often lost to recombinations, emit the light, etc. So the efficiency can be low. And again, separate the charge needs to transport to find their way to the corresponding electron being collected. So if you look at the steps, and each converging step always involves a lot of loss related to various mechanisms. So really, from device point of view, when we look at the materials, device design, or characterize the devices, you need to carefully characterize, understand the process of all these loss mechanisms. Hope that you design approach to overcome them, therefore achieve a high efficiency. So this is the end target. So for organic semiconductor organic, it is called organic because the molecules in the materials are carbon-based, like the molecules in the living things. This is opposed to conventional inorganic semiconducting material like silicon or copper that we use in conventional silicon solar cells. So the photo generation, charge generation, the device operation mechanisms is different from what we know. So from optical point of view, as I mentioned earlier, that the active layer thickness that you need for an organic solar cells is relatively thin, low. So assume that if you look at this cartoon, if this is the thickness of glass substrate, typically 1 millimeter thick glass plate with ITO, then you have layers of organic materials. Finally, you have cathode. So if you look at this stack, essentially they can be considered as a thin film system, right? So when light strikes on the substrates, you have refractions. So some of the light will penetrate and gets absorbed by the or different layers, and eventually gets reflected, bounce back from the reflective cathode. Typically, silver or aluminum is used. And so, really, if you want to optimize the devices to have a high efficiency, one way of look at the system is that you want to understand how does the light distribute within this multi-layer system. You want light you want to absorb most of the light in the area where they can generate excitons there for possible high efficiencies. So really, if you understand the distribution of the light in this thin film system, will help you to design organic solar cells with high efficiencies. Okay, so one way of doing the different optical approach. One way we found is very convenient to do is so-called optical admittance analysis. So essentially, when you deposit the first layer, then you have two interfaces, and when you deposit the second layer on the first layer, and then essentially the second layer can seize the first layer, and the substrate can be equivalent to one surfaces. Okay, so this is called admittance analysis. So provided essentially theoretically this works for a system with any layers, so long as you know the optical properties of those materials, then you could simulate, understand how does the light is propagate, and where they generate most high optical field. Therefore, you want to adjust the light propagation in the system such that most of the light is located in the bland layer, for example, or photoactive layer, where you want them to be absorbed more efficiently. So in this work, that first of all thing you need to do is that to get N and K values of blend layers, essentially, and all the layers, and you can measure, and then use this as a basis so you can calculate the light propagation in the systems. Okay, and as I mentioned that for organic materials, organic semiconductor, because one of the limitations is that the absorption profile is very low, narrow. So in order to have a high efficiency solar cells, one approach is that you can stack them together to form a tandem solar cells. So you have subcells which responds to different parts of the solar spectrum, and then you stack them together. So entire stacked cell becomes response to the light in a more broader range. And when you stack them together, essentially you need to have a interconnector. This is what we call the interlayer. So this interlayer has to be transparent, highly electroconductivity. Otherwise, it won't be able to pass the charges around. Okay. So there are essentially three types of so-called transparent interconnectors. One simple way is that you deposit a very thin layer of metal to connect the two cells together. But this has a problem because a metal layer has a good conductivity, but in general, if you want this layer to be transparent, it tends to be highly discontinuous, and then also it also reflects near infrared light. So therefore, you see that you want something that in between to connect. So when the light passing through, part of the light will be absorbed by the front cell, and those light cannot be absorbed or utilized by the front cell. You want them to 100% penetrate through to be captured by the rear cells. If you have an interlayer which reflects near infrared light, basically blocks the light, so you won't get much of the light penetrate through the first cell. So this is something that really we need to look into it if look for high efficiency organic solar cells. The other one is so-called oxide and organic interlayer. So some of the oxide, when you evaporate it, has a relatively good conductivity and is also transparent, but there's still a limit in terms of lateral conductivity because essentially the current will passing through. And in our group, we use a material called transparent conducting oxide. Essentially, it's ITO or indium doped zinc oxide, for example. This is very suitable for application in that kind of devices. And this we can deposit a high quality transparent conducting oxide on the oxide material that because it has a very high conductivity and also very good transmittivity in the visible wavelength range and until all the way to near infrared. So this is very useful, and depositing of ITO or sputtering of ITO is a very well established technique. It can be easily explored and expanded for application in future mass production. So this is one of the devices, photo of the device that we made. This is a semi-transparent light emitting device. It essentially works the same, and so light passing through, and this is a mirror, and you see that this is a technique that we use ITO for both sides of the devices. Now we apply the same technique for application in organic solar cells. Now the reason why semi-transparent organic solar cell comes in is that a semi-transparent organic solar cell unit is essentially needed for application in tandem solar cells. Okay, so now you can imagine what happens that if I remove the top part, only focusing on this cell actually is transparent solar cells. Okay? It only absorbs what's needed. So you can carefully select the material, for example, only absorbs near infrared, and you design a near infrared mirror here, so the visible light can still penetrate through the entire stack, but absorbs the light and generate electricity. So this is something we call transparent or semi-transparent solar cells, depending on the material that you use. So I need to talk about how to deposit or fabricate a high-performance transparent conducting oxide materials. So essentially, for highly conductivity or high-quality interlayer that you use to connect the top and bottom cells in a tandem organic solar cells, this is essentially the criteria, the technique you need. First of all, it has to be very conductive and very transparent, and has to be very smooth, because we know that the organic semiconductor materials, is particularly in organic solar cells, is very thin. So if you have a spike, basically will kill and create shorts in the solar cell. Second one is it can be easily done. Eventually, what you've done in the lab can be easily transferable for mass productions, and has a very good connections, adhesion to the substrate underneath layer, and then has the flexibility for different sizes and shape and high volume. This is mainly for future, because we are doing research in the lab, but we also need to look at what the outcomes of our research are very good, and whether they will be likely to adopt by the industry for future application. So this is areas is quite attracting, and for various for flexible OLED display, OLED for lighting, organic solar cells, and sensor application. So we actually spend a bit of time to develop this technique for various applications. So the technique I call is called low processing temperature. Currently, I believe that some of your the researchers may have already used ITO coated glass substrate for your solar cells fabrication. But ITO coated glass you purchase from vendors, they basically deposit using sputtering process or magnetron sputtering process at a high temperature, and for 200 degrees Celsius if you want to have a good ITO film on glass substrate. But this technique cannot be used for application organic solar cells. We know that these organic materials, they cannot be prepared at such a high temperature. So we developed a technique called low processing temperature, and essentially they operate at a room temperature, so compact very good with the organic semiconductor materials. So this is the carrier concentration and mobility of the ITO film prepared at different conditions. And the whole idea here is that we include using reducing gas species during ITO fabrication. In most of the cases, if you've done ITO, ITO is typically prepared with the presence of argon and oxygen media, because you want to get a sputter done in this. And in this work, we introduce a very small amount of hydrogen species, serving as reducing gas during the ITO deposition, because ITO is an organic, is an oxide semiconductor materials. You know that in semiconductor materials, the doping controls the conductivity of materials, while in ITO, this semiconductor itself, the dopant is controlled by the indium, tin, and also the oxygen vacancies. So during the fabrication of ITO, if you'll be able to control the oxygen vacancies, and oxygen vacancy theoretically controls 2 free electrons, then you can tune the conductivity. Of course, there has to be in the optimum range. If you remove too many oxygens or created the oxygen concentration vacancy is too high, then you have a mono reduced material, then it turns black, and this is not what you want. So you show that the black curves here I show here is the sheet resistance as a function of the hydrogen partial pressure that you use. It's a very small amount of reducing gas spectra. So you could tune because the conductivity or the sheet resistance is essentially the product of carrier concentration and charge mobilities. And so you see that there's a large window where you can tune the conductivity or the material where you achieve lowest sheet resistance you can have for the solar cells application. Then you can use that for application as an interlayer in integrated or the stacked solar cells. So the other things we found is very interesting is that as say this is the transmission spectrum measure for sets of ITO prepared with the different concentration of hydrogen gas in the gas mixture during the sputtering processes. And there's a clear so-called blue shift the cutoff and the short wavelength range. So this is very useful because when we use organic, this is typically good for display application. For the organic solar cells, if you're using conventional, which is the black solid line curve here, and the absorption in the short wavelength range is typically around 50%. And the ones with this technique, you'll see there's a clear shift, a blue shift. So the dotted line at the same wavelengths, the transparency is much higher. It can be increased from 50% to 80%. Now this is not probably for organic solar cells is not big in a deal because you don't have much of the photons in, and many photons in this range. But for display, it is very important. The blue emits, for display essentially the three primary colors: red, green, and blue. And the blue efficiency of the OAD with a blue OAD usually has a very low efficiency. So for ITO, if the blue part has a lower, you can improve the transparency for the blue light, deep blue especially, from 50 to 80%. This is very, very good for OAD-based display applications. Okay, so this is essentially the parameters that we use. And this ITO can be using the technique that I just described, can be prepared at a temperature less than 60 degrees Celsius, and we'll be use this on the plastic substrate for light-emitting devices, for flexible solar cells, and also for semi-transparent solar cells. So these are the parameters: 85% transparency, and for 130 nanometer thick ITO, the sheet resistance about 25 ohms square. So this is very good because this is a room temperature prepared. So ITO is amorphous state, so it's very, very smooth, and you find a lot of applications. So the technique that you deposit has no damage or very low damage to the underlying functional material. So you can use for solar cells and for other things, light emitting devices. Okay, so now I'll move on the how to tune and optimize semi-transparent organic solar cells. So here is the cross-sectional view of a stacked solar cells, tandem solar cells. So essentially you have a glass, you have indium tin oxide, a transparent electrode, you have one cell, subcell, you have an interlayer, you have top cell, and then you have a reflective cell. So if each subcell responds to different parts of the solar spectrum, and then the stacked cell will have broader responses to the solar cell, therefore have a high efficiency is expected. So what happens that if I stop device here or only design device in this part, essentially you see a semi-transparent solar cell. So this is an actual solar cells fabric made up to here. Okay, so you can see through and still see, but it absorbs the light and also generate electricity. Okay, so first thing we probably will look into is that looking to how does the how much light is being absorbed in an actual we call the opaque cell. It's a conventional cell where you have a very thick layer of reflective cathode. So what we do is that you calculate that we call the integrated absorbance. That means that the all lights that the light being absorbed by the active layer in an organic solar cells as a function of its thicknesses. We want to scan the thicknesses around and see how does theoretically how much light is being captured by the cells like this. Okay, and experimentally it's very tedious because you need to control the time and doing very thicknesses. It's quite complicated and very difficult to do that. So theoretically, using the optical admittance method that I mentioned earlier, and you can calculate because you're only interested in the absorbance in this region, the blend region. So you could calculate the integrated absorbance as a function of the thicknesses, its thicknesses. So you can find that this is the absorbance of the layer in the bland layer oscillates. Okay, so you find that it's very interesting that in certain layer thicknesses, for example, here close to 75 nanometer thick bland layer has a relative maximum in terms of light absorbance. And the further increased layer thicknesses, for example, to 120 nanometer, means that cells, if you're using 120 nanometer thick bland layer, it does not absorb more light than a device with a thinner layer. Okay, this is because of the interference effect. But we know that for organic semiconductor material, because the mobility is relatively low, so a cell which absorbs the same amount of the light or even high light, you can with a thinner layer, which is more preferable. So it depends on the application. If this is a tandem cell, probably you need to look at maybe a layer corresponding to that kind of relative absorptions. Because this is only for P3HTP PCBM bland. If you're using, for example, PCD-TBT C70, for example, probably the peak will be located in various places. But essentially the physics is the same, right? So when you're looking into another relative maxima, you see that if you choose a layer thickness around 225 nanometer thick, then you're likely to absorb 50% of the light in these devices. So if you're looking into a bulk opaque and not single junction cells, probably this is the layer thickness you're looking at. Anywhere differ from this is not going to guarantee that you will get maximum absorbs maximum of the incoming light. So this is very interesting. You can calculate it very easy to do. So for tandem solar cell, using the same technique, probably we're looking to look at the devices corresponding to that kind of the thicknesses. This is the area. Experimentally, you can select few fabricate a set of devices with selective layer thicknesses in this region. Okay, so we can look into a little details and why my 75 nanometer thick devices absorbs more light than the device that has 100 nanometer thick. That's because of this is a thin film system, so it works with interference effect. So for incoming light, if you can adjust the thickness right, then you have a maximum absorption peaks located in the bland layer. That's the reason. If it's slightly thicker off away, then this peaks shifts either in ITU or P dot, where although the maximum absorption, the maximum light field could occur in this area, but they don't generate excitons. That was the reason why. So this probably the area we're looking. So we compared a lot of reported literature results, and experimentally, if you were looking into high efficiency and this system-based solar cells, and you will find that this agrees with the simulation very well. Yeah. So this gave us some foundations. So now we start looking to semi-transparent solar cell. Probably this is the area, the layer thickness we should look into. Yeah. So as I mentioned, that for tandem solar cells, you need to have additional stack. So theory idea is the same, and for the light which is not useful for the bottom systems, because organic semiconducting material has a relatively narrow absorption spectrum, and then you try to encourage the system to have more of the light penetrate through, so be recaptured. For semi-transparent solar cell, the idea is the same. So we want this thing as transparent as possible, but at the same time also absorbs the maximum incoming light. Therefore, I have a system that transmits the light and also generate the electricity from the light. So essentially, we're talking about two competing performance indexes for semi-transparent solar cells. So first thing we look at is that, again, looking into the absorbance of the bland layer in this system, and we scan the layer thicknesses, looking the deposit ITU. So we know that without upper organic stack, the transmissions is essentially determines by the it's dependent by the layer thickness. So we scan absorbance of this layer as a function of the ITU the ITU layer thicknesses. Then we found that this absorbance in the layer modulates in this way. Okay, So there's a maximum absorbance could occur if the top layer, top ITO layer thickness is in the range of 70 to 80 nanometers. But we say that this is a semi-transparent unit. At the same time, we are also interested in looking at how transparent this can be. Okay, at the same time, we are also looking at the transparency of the cells as a function of the ITO layer thickness, and it follows that way. So it tends to agree that if we only select the thicknesses. The ITO thickness according to the maximum absorbance, probably this is the maximum absorbance, but then you won't get a very good transparency. So in order to optimize both, probably we need to take care of both probably in the actual applications. And so long as you select the layer thickness in these grain regions, and then you probably get a device with both high transparency and high absorbance. Okay, so anything away this probably either you lose the transparency or you lose the absorbance. So this is how this is selected. This paper was published a few years ago. Okay, here is the parameters, and we have external quantum efficiency of control devices, which is made on the opaque, very thick, around 200 nanometers. And then we reduce the layer thickness to select 75 nanometers, and for semi-transparent, because this is where absorbance spectrum has a second, has its first relative maximum absorbance. And then we fabricate a set of the devices, and we found that for a complete control, non-opaque, non-transparent, opaque control device, this was a little bit old data. Now we can get over 3%. This is a 2.8%. And then device B is also a control device fabricated with 75 nanometer thick bland layer, but with a non-transparent aluminum layer. Then we see this is the maximum you can get about 2% with this thin layer. But if you replace aluminum with ITO, then you get about 1.8%. At the same time, this device is about 40%, 30% transparent. So this is a very encouraging results. Okay, so we expanded work to include other systems. Essentially, the physics is the same, so do the same design, and now we look into small molecule devices, zinc PC based. This is a sublimated device, sublimation through thermal evaporations, and in this system we found that the maximum or the common agreeable layer thicknesses for top ITO in terms of agreement between the absorbance and the transparency is about 40 nanometer. And then this is the black curve, is the transmissions of the entire devices simulated, and the red one is measured, because when you finish the device, you can always measure the transparency of the devices. They agree very well. So this is the opaque devices, and you replace with transparent ITO devices, you get this efficiency. So this is a control device with aluminum and 4%, and you replace the aluminum with ITO, you get about 3%. So it's a very good agreement, and in terms of theoretical simulation, research agreement. So essentially, this technique is very useful. You can apply this for other systems as well. Provided the different system that you use, the bland layer you use, probably you need to tune the different optimum levels, but you know the technique, then it becomes very easy. Otherwise, experimentally, you try and error. Maybe I'll spend another couple of more minutes to discuss a new project we are doing now to apply semi-transparent organic solar cell for application in switch type of devices. Now, in our group, we also work on the OLED, and now what happens that if I have semi-transparent solar cells, another solar cells, you stack them together, this becomes a tandem solar cells. Now what happens that if I remove the top solar cells, and then this becomes the semi-transparent solar cells, and then I stack another device, which is not the solar cells, is a light emitting diode, organic light emitting diode, which is also solution processable. Then it becomes that kind of things. Now this has a function, reason. One thing is that if the front layer is the organic solar cells, and then you can choose the material in such a way. This is the external quantum efficiency, IPC spectrum of this semi-transparent solar cell. OAD emits the light, of course, and then you select a material, emissive material, as well as the solar cell material in such a way that you allows to choose the emissive EL spectrum, the peak, located in the valley of the IPC. So it is very interesting when you essentially put an organic solar cell on top of a light emitting diode. It doesn't block the emission efficiency because it only absorbs the light which is outside the emission spectrum. Now this is very useful for I think some of you may have OAD based handphone display. If you read the OAD display under the strong sunlight, because it reflects, if without this layer and the light, ambient light gets reflected, and you can't see the image very clearly. Now if you have a devices with that kind of structure, and no matter what ambient condition is, and when you read a message, if it is a strong ambient sunlight, and it won't reflect because it absorbs by the front cell. So therefore this display has extremely high contrast ratio, and at the same time the turned unwanted light, basically this part of the light disturbs the visibility of the display, and then it convert them into electricity. It can also charge your battery as well, and this is something that's very interesting. We're looking at the second one is that instead of stacking them together, you put on both sides of the glasses, and you have OAD and you have semi-transparent solar cells. You connect with a transistor, and then here is the organic OAD, organic light emitting diode, and then at the 4 or 5 volts emits the light. Now what happens that if you turn it over and you have OAD in the front and OPV in the back, or in the other words, and then this light coupled into the integrated semi-transparent solar cells, and this will instantaneously generate a photocurrent. And then you can have a resistor here, and when a photocurrent, there's a voltage drop. If you could design the system and select the appropriate resistor, and the voltage drop in such a way that it just slightly above the turn-on voltage of this transistor, and then the entire system will be on. Okay, so how does it work? Then you could apply, say, a few volts, and initially there's no current here, so there's no current passing through. There's no circuitry, so the OAD is not is off, is not turned on, and there's no light. So what you could do is using the laser beam, for example, and you shining a light passing through, because these are all semi-transparent solar cells. You could do both ways. It depends on how the arrangement is. And then the light passing through semi-transparent OAD or OAD, and strikes on the rare organic solar cells, and then just initially they generate a photocurrent, and this photocurrent will strike, and there will be a voltage drop, and then at the same time, as the moment you turn the laser beams on the devices, and there will be instantaneous photocurrent generated, and there will be a instantaneous voltage drop, and if the voltage design is above the turn-on voltage, and then this whole things will on because there are current passing through. And the moment you remove the laser point, because this is already turned on, at the same time the light coupled into organic solar cells will continue to supply the current. So essentially the whole system was off and switched on, then it can be turned on by shining a laser. So essentially there can be kind of a photo switch. You know, if you want to turn something on, you just shine this and then the entire room is on. So this is very useful for display application, and can be also used for image control, and also for intensity control. So that's slightly beyond the scope of this talk. And just to let you know that organic semi-transparent organic solar cell can also be used in that kind of application. Okay, so this is the photo IV curves of an organic solar cell, semi-transparent solar cell in this case, deposited in front of an OAD. So you see that the dark one is the IV characteristics. The one with the green curve is a separate organic solar cells. And this is the IV curve. So you see that essentially it doesn't interfere with the OAD with a very nice efficiency. Okay, I think this is probably my last slide. A quick summary. Okay, so organic semi-transparent solar cells are introduced admittance analysis technique, and then if you know the transparent electrode, you can use for many interesting applications for lighting. And the semi-transparent solar cells, compared to conventional silicon-based solar cells, can be mainly used for power generation windows, and maybe for building surfaces and windshield and tension membranes, where you want the things can be more flexible and low cost. So I'll stop here and thank you for your attention. I'll be happy to take some questions. Thank you.